dynamics over a circular domain. There is a circular domain, and if we pass the fluid above this over this circular pipe, then the fluid passing through like this way, and this is known as streamlines also. So we can show this picture for understanding the computational fluid dynamics problem. Actually, design, analysis, and design purpose, also knowledge and exploration purpose, we can use this CFD problem. First of all, anything when we start to research, then it is cost or a full-scale simulation, or like shapes or deep geometry. And also there are sometimes for when we do experiment in all countries, we don't have experimental facility, and that's why sometimes we can't go for experiment. And also for experiment, it is sometimes environmental, some effects arise, like wind speed, like weather. Sometimes these are not in our favor, or sometimes hazards also happen, like explosions, radiation, pollution, etc. And sometimes the prototype is not, to make prototype is not possible, like planetary boundary layer, stellar evolution. Computational fluid dynamics comes forward to build and test. It is more cost effective and it provides high fidelity database for diagnosing the flow field. Even from CFD analysis, we get many data like 2,000, 3,000, 1,000 data. Then we can use this data by machine learning approach, like artificial neural network, or statistical analysis like response surface methodology. And then we also get some optimization, and also correlation coefficient, more better correlation coefficient independent variables. That's why for the data source, for getting more data, we can use actually computational fluid dynamics. So where we can use this type of computational fluid dynamics? There are many sectors in our environment. We can use this, like aerospace. Here, the figure shows S1H state separation problem, and right figure shows for biomedical sector. Here, this is a eye following measure heating temperature. By the geometry, and this is, you can see the automotive, when the vehicle go forward, then the flow dynamics over and beside this automobile, you can see by this image. So there are another sectors like chemical processing. Here we can see polymerization, reactor vessel, prediction of flow separation. We are seeing here the flow separation figure and residence time effect. Also, this is the HVAC, we all know that the HVAC, heating, ventilating, ventilation, and air conditioning. Also, this figure shows the streamlined pattern for the workstation of HVAC ventilation. And also, the right figure, this is the hydraulics, and we see here they score downstream of and the downstream is shown by this figure. And also for marine sector, we can analyze it for shipbuilding, ship design, hull, or many things for in the purpose of this ship. We can use the computational fluid dynamics and here for sports sector, when a bowler in the cricket match or when a bowler throw a ball, then the ball passing air pattern over the ball. You can see there. And also this is the chemical industry where oil and gas are produced or over drill bit, and this sector is very much important in our chemical industry. And this is also power generation, flow around the cooling tower. We can see here around the cooling tower what type of flow flow becomes. We can imagine to see this picture also. And CFD process, there are a few processes here. First of all, we have to choose a geometry and then geometry parameters and its domain and size. We have to select, and then we have to select again physics, what type of physics we can consider, heat transfer or it will consider or not, or fluid flow it will consider or not. If fluid flow is considered, then we have to select flow properties, discuss model, boundary conditions, initial conditions, etc. And after that, we can complete our mesh structure. It may be structured mesh or unstructured mesh. If we use finite difference method and for numerical simulation, then we get structured mesh. And if we use finite element method for simulating a numerical purpose, then we get unstructured mesh. Okay, after that we have to solve the model, mathematical model. It may be steady or it may be unsteady. Then we have to set number of iterations or steps, then convergent limit we have to choose, and precision after how many points after the decimal we need the precision, we have to select it. And numerical scheme can be completed. Then reports we can draw XY plot, and we can verify our result with other published results. Also validation can be done, and after that finally post processing we can draw contours, we can draw vectors and also streamlines, and also temperature, surface temperature, volume temperature, and many more things. Also slice plot and many more things we can draw as post-process. Is an initial and boundary value problem actually, and for initial and boundary value problems we can use partial differential equations. These are non-linear. Actually, in our environment, next maximum events are nonlinear, and it depends on many more factors. And that's why our partial differential equations are considered as well as boundary conditions we have to set. And maybe there are many more geometries built in software. You can draw it like if you use console multiphysics for numerical simulation purpose for finite element method. And then there are many default geometry here, but you can also draw complicated geometry. You have straight, and it may be two-dimensional analysis, it may be three-dimensional analysis, it may be Cartesian coordinate system, also can be cylindrical coordinate system, also can be spherical coordinate system. So based on your geometry, research geometry and research topic, you have to draw geometry, draw set, domain, and mesh also in your software or computational technique process. And you can see this is the Cartesian coordinate system, cylindrical coordinate system, also spherical coordinate system, and general curvilinear coordinate system. It transferred to the general orthogonal coordinate system. So we have these five types of systems. So you can use two-dimensional or three-dimensional analysis. And Navier-Stokes equation, it's most important equation to it may be air or it may be any kind of liquid. So to understand the flow dynamics, fluid dynamics, we need an Navier-Stokes equation. It is shown here in three-dimensional Cartesian coordinate system, and the first term is the local acceleration term, and these three terms are called convection terms. This is the pressure gradient terms, and this is the viscous terms. And the equation of state is given by this equation. The continuity equation is given also here, and the Rayleigh equation you can see here. Rayleigh equation. And modeling, for modeling, we have to understand first that our model or our system is viscous system or inviscous system, or here it is turbulent flow or laminar flow. Is there any external flow, or only it can conduct internal flow? It is compressible or incompressible. Compressible fluid like air, incompressible fluid like water. It is single phase flow or multi-phase flow. So many things we have to consider for computational fluid dynamics modeling. We consider or not, free surface flow or surface tension we consider or not, is there any chemical reaction or combustion system we consider or not. So many things we have to notice at first before starting the simulation. Model our physical modeling, and then after that we have to select initial condition. So initial condition, there are shape reports are usually run in the steady mode. That means there is no time dependent matter, but in nature you can see all the phenomena are time dependent. So time-dependent analysis is known as unsteady flow problem, and steady mode is is easier than unsteady problem. So we can say when we consider unsteady problem, then initial condition at time t equal to 0 second or 0 minute or 0 hour, what is the condition, and how many time, how long we can conduct, that is from 0 second to 50,000 second or 40,000 second, whatever you want. You have to mention all these things. And also boundary condition in any kind of geometry. When we set, when we draw, then we have to put our boundary condition. You can see that this is a circular pipe. This is a pipe here. The blue color mentioned the inlet fluid, and the red color shows the outlet part. And if this is a three-dimensional phenomena, but if we cut this domain along horizontal axis, then we can draw like this is a rectangular part. So the middle line is the symmetric line, axisymmetric line. Due to time consumption, also our computational facility, also our computational time, and your computer configuration, and many more things are dependent on this. That's why whenever we can see that our considered geometry can be transferred to from three dimension to two dimension, and then we always go for two-dimensional analysis due to the previously mentioned factor. We go for, and the dot line is axisymmetric, and the flow, this blue part is inlet. This
So, dear participants, there is a small technical issue from Madam, and Madam is again rejoining. Please. Madam is rejoining. Please hold on line. Sorry for inconvenience. Ma'am, you are visible, ma'am.
Yeah.
Yeah, PPT is also clear, ma'am. You please proceed, ma'am.
Okay. You can see my screen.
Yes, ma'am. Yes.
Okay. Thank you. Sorry for the disturbance. Actually, okay, thank you. I am again starting. Okay. Okay, for discretization methods, this is two-dimensional incompressible laminar flow boundary layer problem. If we use finite difference method, scalar box scheme, then we can go for these types of solution process. And here, this is the continuity equation. This is the momentum equation. You can see, and this is the momentum equation. Here, this is the viscous terms. And for using the Kähler box scheme, we discretize this second order partial differential equation into these forms. So finite difference, this is the forward difference process, and this is the backward difference process. And the first order terms, like del u by del x, del u by del y, these terms we can discretize also by this way. This is the first order term, and the accuracy is 1. Here, the 2. And finally, after discretizing all the equations, finally we get a matrix. And to be stable, this matrix has to be diagonally dominant. And solving it using Thomas algorithm process, and we use solver, and for solver can be either direct, like Cramer's rule, Gauss elimination technique, LU decomposition technique, or iterative process like Jacobi method, Gauss-Seidel method, successive over relaxation method. We can use any of these methods. And for numerical parameters, under relaxation factor convergence limit, we have to select different numerical scheme. We can choose. We can monitor also the residual changes and also number of iterations to become steady, to get steady flow from unsteady wave. And single or double layer precision we can select. And if we use finite difference mesh, I told you to use that, or then we get structured mesh. This is known as structured mesh. And if we use structure, here the thin boundary layers best resolve with highly stressed structured grid, and there is an unstructured based on the pressure gradient or regions interested. So we can use Fluent software, or we can use functional multiphysics software for making our mesh generation. and grids can either be structural, like hexahedral, or unstructured tetrahedral shape. And this is a physical domain. You can see if we transfer this domain here in a rectangular system, then all the grids are structured grids. And transformation XYZ, that is Cartesian coordinate system, to the computational domain xi, eta, psi, like this way. So 2D as an example. And here I am showing you. And for visualization, the contour, the velocity vectors, streamlines, grid lines, path lines, streak lines, and isosurface in three-dimensional space. We can go for these types of figures, and CFD analysis for verification and validation using experimental fluid dynamics data. We can use, if we have available, if we get experimental data from any source like publications or any kind of source, then we can compare our result or validate or verify our result, our computational fluid dynamics result with experimental results also. And here we see that the isosurface of the physiometric pressure free surface color using Z for fully appended antenna. And for this visualization, we can use Techplot 360 software also. For commercial CFD code, Fluent maybe Star CD, it also used CFDRC, CFX, AEA, etc. And research CFD codes, CFD ship, IOWA, public domain we can get, and other CFD software includes the grid generation like GridGen, Gambit, and Techplot, FieldView, etc. So there are many software we have. We can use these softwares for computational fluid dynamics purpose, simulation purpose. Now I am showing my few published research where I used many kinds of practical geometry or apparatus to get more a shell and tube kernel exchanger with case Crawford model. It is published in 2021 Journal of Nanophysics journal. So here you can see the outer surface is the shell. It is known as shell and tube heat exchanger, thermal exchanger or heat exchanger. This type of geometry commonly used in chemical industry or chemical engineers. They use this type of apparatus. So outside, this is known as shell. There are shell inlet, shell outlet, and inside there are many tubes. These are known as tubes. So there may be tube inlet and also there may be tube outlet. This picture I just taken from Google source. So I am showing you my paper where you can understand how the finite element method is used to model the nonlinear partial differential equations, actually coupled equations or system of equations, where we can analyze fluid flow, heat transfer, and also try to find out the thermal efficiency of also this kind of useful apparatus. Okay. So I am showing you. You can see my paper, published papers. Can you see? Hello?
Ma'am, it is visible, ma'am.
You can see well? It is visible?
Yes, ma'am, it is visible. It is visible, ma'am.
Okay. 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 Or can I make it larger?
Ma'am, it
Okay.
is okay, ma'am.
So,
It is clear. It is
okay.
clear.
Okay. Thank you. So it is here in this research we actually consider turbulent and laminar flow. When we go for a sea beach or sea or ship then when a ship moves, then beside the ships the fluid becomes white and many more sections and white color foam arises. This in this case that creates turbulent flow. But at the few long distance, if we consider long distance flow from then the water becomes bluish and it is a steady, normal flow. There is no foam, there is no white color, no friction. So in that case, there is a laminar flow. So when turbulent flow occurs, then we have to choose the turbulent flow analysis model. There are different models for turbulent flow analysis. For example, Reynolds Everest Navier-Stokes equations are commonly used to analyze the turbulent fluid model. Okay, here we use nanofluid. Actually, nanoparticle when nanoparticles are mixed in a fluid like water, like oil, like kerosene, then they are created nanofluid. Here we use multi-walled carbon nanotube because its thermal conductivity is high, many more high than water. Thermal conductivity of water is maybe 0.6 watt per meter Kelvin, but thermal conductivity of multi-walled carbon nanotube is almost 400. So we use this multi-walled carbon. Turbulent flow analysis, we use Case-Crawford model. Okay, then we go. I am showing you how we use this type of model into two-dimensional geometry. Here you can see the model geometry. This is the three-dimensional. I only consider the inside the pipe also, and outside there is a shell. And inside there is a tube. There are many more tubes. So this is known as shell and tube heat exchanger. So this is the three-dimensional geometry. And the right part, you can see this is if we cut our geometry like this dot line, then we can go. We can create like this pattern. So we consider this pattern also. You can see this is the pattern, and the gray color, inside the gray color, the fluid passes from top to the bottom, and the half circular part at the half part of a pipe of a tube. So this is shell and tube heat exchanger. In this way, we consider a two-dimensional model. So for computation, to reduce computational cost and time, here you see this is 1000 millimeter scaling, but we take just one part only to reduce computational time and also computational cost. So this is the computational domain. So this circular part is the pipe boundary, and the free pipe domain. So here we use turbulence, space Crawford turbulence model, that is known as analysis to analyze the turbulent model. You can see the equation 1, 2, this is the continuity equation, equation 2, this is the momentum equation of X momentum equation, equation 3, Y momentum equation, and all these are partial differential nonlinear displays. And equation 4, this is the Space Crawford model. Equation for turbulent K epsilon model. Epsilon model is equation 4, and equation 6 is the energy consumption equation. So there are 6 equations. We can handle these 6 equations at a time. And here the dependent variables are U, V, kappa, epsilon, T. There are 5 dependent, T and also P also, pressure. There are 6 dependent variables. These are known as space variables. So there are many these equations in the COMSOL multiphysics, and we use finite element method. 8, also equation 8, 9, 10, we use this equation. Equation 8 is known as Reynolds average. Maybe 11, 12, 13, these equations are nanofluid related equations. That means effective properties of nanofluid. And for calculating average heat transfer rate, we use equation 14. And we have to set border setting, that is boundary condition. These are the boundary conditions. And here we consider only steady state conditions. That means time mesh generating part. We see the mesh generation. This is the normal mesh. There are various types of mesh, like extra coarse mesh, extremely coarse mesh, normal mesh, fine mesh, finer mesh, extra fine mesh. There are 9 or 10 types of mesh. Normal mesh and also fine mesh. There are 2 types of mesh we show here. So the circular part is the boundary of tube, and this is the flow domain. And after that, we show here code validation. We validate our code to Safarian et al. And because it's a numerical simulation or numerical analysis, so before going publication, we have to validate our code, our present code, so that no researcher or no reviewer can query about this part. So after that, we go for grid sensitivity check also. I told you there are different types of meshes, and when we go for finer type of mesh, then the time takes more. this is 464 seconds, but when we go for fine mesh, this is 2. You can see the Nusselt number value, that is the heat transfer rate, is not significant. We use a fine type of mesh here to reduce our computer configuration, computation cost and time also. And these are the contour plot. This is the streamline plot. For visualize this plot, we use TechPlot 360 software, where we can directly extract data from the COMSOL multiphysics and import it to the TechPlot 360 software. So we don't have any kind of tension about data extraction. Directly, TechPlot 365 software can use by importing data from COMSOL multiphysics or ANSYS software. So this is the streamline visualization. Middle one is the isothermal visualization, and the last one is the surface velocity plot of the surface. So these are the visualization part, that is post-processing part. After that, we can show some figure using Excel software for data extract from using data extracting from COMSOL multiphysics or ANSYS software, and as CSV file. There is that CSV file we can software for data plot. So we can see here these are the all data plots, also surface temperature plot. And we can conclude that for this we can conclude the remark that another thing I just forgot. This is the comparison part. Reviewer always search whether in the manuscript comparison part is exists or not, because this is a numerical analysis we cannot do for experimental analysis. So our results, our simulation results should be compared to the other published numerical results or experimental results, whatever you have available in the literature. So this part is mandatory, or this part is necessary to establish that your result is nearer or accurate, or there are not significant difference from the previously published results. So here we just compare our results with few published results like Young and Liav-based Reynolds number, and percentage of error also shown here. The percentage of error are like this, and the lowest percentage is 1.05%, and the highest error percentage is 5.33%. So this is Young and Liu, and this is the present result. So this top part is also very important. And also conclusion. And here we conclude that the main conclusion is higher rate, approximately 12.24% of heat transfer is obtained using water-based carbon nanotube with 3%. If we use clear water, then we get a 3% lower heat transfer rate. 12.24% lower heat transfer rate. And here the nanoparticle nanoparticle solid concentration is used as 3%. That means total, if we have 1 liter of fluid, then 1 liter of fluid, then 0.97 liter fluid are used for 97% fluid used as water, and 3%, only 3% we use multi-wall carbon nanotube, nanofluid, and nanoparticle as powder form. Always nanoparticle are as powder form, and when we mix in the base fluid, then after few connectivity, and then we get the nanofluid. And for this purpose, we use few machines like where I don't know, in my university we have no apparatus for experimental purpose like this type of experiment, but in first world country there are of course some experimental facility where they can make nanofluid. They can just buy nanopowder from market, and then they have machineries to mix the nanopowder and the base fluid, and after that they shake it well and perform the experiment. But in my country we have not such kind of facility. So this is one research paper I have. Another one, I am going to my presentation. This is, you see, this slide. You can see this slide. This is another paper. Here, numerical appraisal of time-dependent peristaltic duct flow using Casson fluid. Here we use time-dependent analysis, that is unsteady analysis. And this figure, you see, this figure, this is a bolus system. When we eat food in our system, from our mouth to our abdomen, when the food goes from our mouth to abdomen, our muscles become relaxed and contraction, relaxation and contraction. This process continues when food going through our channel. So this is known as peristalsis and flow, and the food is known as bolus. From ball to this word comes as bolus. So we can go outside to run the system. So when we eat food, then this system occurs in our abdomen, from mouth to our abdomen. So this is muscle contraction and relaxation system. Can you see this slide?
Yes, ma'am, it is
Hello?
clearly visible, ma'am.
Okay, so I'm going to my presentation again. Okay, so now I'm going to show you shortly, very short way. Prof, please just tell me how many minutes you have. Then I will short my presentation. Okay, so this is the Casson. Here we use Casson fluid. It is non-Newtonian fluid. Actually, Casson fluid, it's named by over Casson scientist, and it is non-Newtonian, like water, air. These are Newtonian fluid, and non-Newtonian fluid like toothpaste, honey. These are known as non-Newtonian fluid. Here, the viscosity is not constant. In Newtonian fluid, the viscosity is constant, but in non-Newtonian fluid, the viscosity is not constant. So in this case, what is our geometry? We just consider our geometry as a horizontal view. This is the horizontal view, you see. So here fluid is passing, and this is the relaxation part when the bolus is here. When bolus go through this part, then this part also, this contraction part also becomes relaxed, and it will continue this system. So for reducing the time and cost management, we just take a single part of the bolus system, total system. So here is the cation fluid. This is the solid body, that is food bolus or ball, like this we can say, and this is the part of extraction part. Here this is the contraction part, relaxation and contraction part. Here inflow, and also here is the outflow. And this is the schematic part of peristaltic duct flow. And for cation fluid, we just use for relaxation part, we use the sinusoidal wave pattern, equation 1, 2, these are the sinusoidal wave pattern, and equation 3, 4, 5, this is the equation 3. This is the sinusoidal pattern, wave pattern. Equation 4. Here we use these equation, dimensional equation into non-dimensional form. And for cation fluid, we use equation 5. This is the well-known pattern, and many authors use this equation for analyzing the cation fluid. And equation 6, 7, 8, these are the governing equations for non-dimensional governing equations. Here we use Reynolds number. This is Reynolds number. That is forced convection number, because when we pass our food from our mouth to our abdomen, we have some forces convection, and these are the boundary conditions. Table 1 shows the boundary conditions of what we have considered, and equation 9, 10, these are also the temperature of the fluid domain, thermal analysis, and equation 10 is the temperature of the solid domain. We consider the food part, that is the bolus part, is as a solid domain. And so we also analyze here entropy generation. How much entropy is generated here? That is, entropy generation is in a single sentence, we can say that it is the system loss. So in any system, there are some system losses. So entropy is the system loss. So our objective is to reduce the entropy generation, so that maximum energy which is produced, we can use our system. So this is the entropy generation part, 11A, 11B, and also this is the non-dimensional equations, that is transformation part, and also these are the non-dimensional number, Reynolds number, Prandtl number. You all know these equations. This is the flow chart. We consider first of all physical model, then we set governing equation, then we set boundary condition. After that, we go for grid distribution. Then we start our model simulation. If we get our convergence criteria, then we can stop our solution, get solution, and stop the process. If we don't have convergence criteria meet, then we start again from this part. And this process is known as iterative process, iteration. So So this is the flowchart of finite element method employed here for the computational geometry, and these are many more mathematical terms. Are shown equation 16, 17, and 18, and so many. And this is the grid test. Here we use 53,736 grid, and supervising variable. As supervising variable, we consider average temperature inside the domain. This is known as supervising variable. So this is the grid distribution mesh where you can see. And for my model validation, you see this is the model validation. For this purpose, we validate our model to the Pope and Sheremet et al. And here we use vertical velocity by the figure A, and average Nusselt number by the figure B, and against average time, against non-dimensional time. Here T tau is the non-dimensional time. We have to consider time dependency also. And here you see that average temperature of the inside the domain. You see that after for Prandtl number variation for red color, you see that when time after 30 is 30, then it is steady. But when Prandtl number 6.8 value, then it is steady maybe after 50. So Prandtl number when 21, then it is steady after maybe 90 non-dimensional time 90 or 100. So for this variation, the simulation becomes steady at various time, after various times. So we have to analyze this steady when our unsteady problem becomes steady. That time is very much important to analyze our flow. So this is the Excel. Using Excel software, we have shown our results into bar chart. This, you can see bar chart also. This is our contour diagram. This is the solid part centered here. This is known as bolus, and this is the fluid passing through Paschen fluid passing over the bolus system, and different time, non-dimensional time at 55, 75. We have shown this type of contour plot. TechPlot 365 software. And also this is the heat line also, and this known as heat line for Prandtl number variation. And in this way, we can show our some figures using Excel software and some figures post-processing using TechPlot software. And also for code validation, we can use this. This is the comparison part. Code validation I previously shown a few minutes ago. This is the comparison part of local Nusselt number and horizontal velocity. We compare this against Khan et al. And also by Rook et al. So you can compare your numerical results with the results available in the literature. And here the conclusion part, you see these are the conclusion part also mentioned here. So this, I am showing you this type of analysis we have done. So many types of various analysis we have done actually in our department, or also in our scholars, masters, MSc, PhD students, and they have done this analysis. And this is another analysis. You can see here the analysis. This is, you see the convergent and divergent channel. And this type of geometry we can see here in nature, like supersonic, subsonic, convergence section, divergence section in aeroplane, rocket, scramjet, ramjet, nozzles, etc. According to Newton's third law of motion, these systems are we actually convergent, divergent channel arises these types of devices like ramjet, scramjet, rocket sections, etc. That's why we consider this convergent, divergent channel, and this is publication is from International Communications in Heat and Mass Transfer in 2022. 22, and I'm going to show you the paper. Okay, no problem. Please goes to the direct geometry. Direct paper. I have downloaded this part, and I am showing you. This is also you can see we use ternary hybrid nanofluid. That is, hybrid nanofluid is a combination of two types of nanofluid, nanoparticles. This is the base fluid and two types of nanoparticles mixing. This is known as hybrid nanofluid, and here we use ternary hybrid nanofluid. That is three types of nanoparticle we consider here, and the base fluid is considered as water and ethylene glycol mixtures. Water and ethylene glycol mixture, and in our geometry is the convergent and divergent nozzle. So we can go for these types of geometry. First of all, I am showing you the geometry part. This is the convergent and divergent part. So here, this is the inflow domain. This is the convergent channel opening, and this is the divergent part opening. This is the outflow part, and the length of the convergent part, the length of the divergent part. This is the contraction part. Here, this is called the model diagram. On the solid part, the no slip condition is considered, and the lower and upper boundary are considered as hot temperature, and the fluid, inlet fluid, it is considered as water ethylene glycol mixture based ternary hybrid nanofluid, and here the fluid is considered as cold fluid, and the velocity we consider fixed velocity to run the fluid from the system. And these are the equations of governing equations, equations of non-dimensional, dimensional coupled system of equations of Navier-Stokes equation of continuity and energy balance equation. There are four equations. So this is a system of equations, and we use this transformation to make the dimensional equations into non-dimensional form. These are the non-dimensional form, equation 5 to 8. And here we use the Reynolds number. The Reynolds number is the forced convective parameter, and this is the boundary condition we have considered. And the Maxwell-Garnett model for thermal conductivity of nanofluid, we consider the Maxwell-Garnett model. There are two parts. One is static part, and another is Brownian part of this Maxwell-Garnett model. This Brownian part here, KB, it is the Stefan Boltzmann constant, and For ternary hybrid nanofluid concentration, solid volume concentration, we consider here equal contribution of three types of nanoparticles like cobalt, like silver, and at the top. This is the top and this is the bottom one. The bottom hot surfaces, we consider the Nusselt number by these. We calculate the Nusselt number by this equation 13. And the ternary hybrid nanofluid properties, these are effective properties we use for simulating these types of solute simulation. And the thermophysical properties, we consider the base fluid as different mixture, like only distilled water, no ethylene glycol, that is 100-0 ratio, distilled water and ethylene glycol ratio 60-40, distilled water and ethylene glycol ratio 50-50, and no distilled water, only ethylene glycol, this is 0-100. So these four ratio mixtures we use for this simulation, and there are three nanoparticles. And this, the mesh is convergent divergent channel. The mesh, finite element mesh, is considered here, and grid convergent. To run the test, grid convergent test, we consider Nusselt number as the supervising variable, and we consider different types of elements, finite elements, and we choose 21,500 elements, and the Nusselt number is this. After that, there is no significant change of Nusselt number, but the elements is higher, and the simulation time also needs more. So we consider only 21,500 elements for this numerical simulation. And these are the physical properties of three nanoparticles like cobalt, silver, and zinc. And this is the code validation part is not shown here. We call a figure, we call a paper our paper. This is so this in this paper the code validation part is shown elaborately. That's why we do not repeat here. And the results are shown in streamline pattern, in isotherms pattern. These are the convergent divergent channel part. Also, this is the streamline profile. These are the isotherm profile, and we for visualizing these we use Stepplot 360 software, and there are few data plot like Excel. So using Excel software, we use average Nusselt number. We calculate average Nusselt number and show also here, and also there are few bar charts for different combination of the three nanoparticles. Which combination is more effective to run the simulation? We can see that 1/6 is to 2/3 is to 1/6. This combination of these nanoparticles are more effective to get higher heat transfer rate. And this is the shape factor, different types of shape factor like linear shape, like triangle shape, cylindrical shape, spherical shape, blade shape nanoparticle. There are different shapes of nanoparticles. We also conduct analysis for shape factor, and here we get that higher values of heat transfer rate occurred when we use linear shape. 16 value of N, it represents linear shape nanoparticle, and also size of the nanoparticle. We know nanoparticle size are from 1 millimeter to 100 millimeter, 100 nanometer. So we consider 5 nanometer up to 100 nanometer, and I get that higher value of Lawson number, that is higher heat transfer rate occurs when we use lower size nanoparticle. The nanoparticle size is lower, then we get high heat transfer rate. So these are the conclusion. You can see here the conclusion also. So this type of geometry or this type of analysis are also most important to conduct our research, because this type of geometry arises in ramjets, rockets, nozzles, etc. So it is very much important to analyze it, to conduct research based on this type of geometry. This is another geometry you see here. This is a liver in our human body, and this part is this part is this part is the this part is the tumor part, and this is the red part is as liver part, and we put an antenna here, ablation zone, microwave cancer therapy, and we perform this research, numerical analogy of bioheat transfer and microwave cancer therapy for liver tissue. Here we use bioheat transfer model, not simple heat transfer model. It is bioheat transfer model. That is the heat transfer model which is used biological body, biological heat transfer. That is any kind of biological body. So I can show you how we perform this type of research there. It is published in Heat Transfer Journal in 2022, and there also this is a little bit different types of analysis. Here you can see different types of analysis. This is microwave cancer therapy. So bioheat transfer model, we use two types of model. Number one, bioheat transfer, and number two, microwave electric current. So the students who are interested in electrical engineering or who is studying electrical engineering, they easily understand this type of analysis. And the students of mechanical engineering, they also understand, because this is bioheat transfer model. So we conduct our research like this way. You can see and the geometry I am showing you. So this is the geometry I am showing you. This is the three-dimensional part. You see, this part is the three-dimensional part. This is a circular domain. We consider a circular domain here, our liver tissue, and there is a tumor here, and we put a coaxial antenna for ablation process. And this is the liver tissue. You see, this is the liver tissue. So coaxial antenna. So this is the slot. You see the slot of the antenna, and it is two-dimensional. This is the three-dimensional view, the left figure, and this is the two-dimensional view, the right figure. And this is the ellipsoidal. We consider the tumor shape is ellipsoidal, elliptic tumor shape. And coaxial antenna, and the whole rectangle is liver tissue. We consider the rectangle as liver tissue. From three-dimensional to two-dimensional analysis, we go two-dimensional analysis. So if we minimize the figure, just to zoom in, then we can see that this is the part. This is the air slot. This is the slot of antenna. There are many parts inside the antenna. This is the outer conductor, inside. This is the central conductor. This is the dielectric part. This is catheter part. Actually, the antenna which we insert in our abdomen, in our liver, doctor insert and this type of antenna in our liver, and using X-ray or using monitors, you can notice everything where the inside the liver, where is our tumor part, and how to abolish our tumor part. So this is the tumor, and inside the tumor we just insert, this is the antenna. Okay, coaxial antenna, and again we consider the right part of the two-dimensional rectangular part of the domain, and because due to minimize the time and computer capacity, we just consider it as two-dimensional analysis. It is RZ axis, and this is the two-dimensional part, computational domain, and you can see this is catheter, dielectric, and many more things, conductor, tumor, etc. And these are the properties of antenna, liver, and tumor. And these are the physical properties. Table shows the physical properties of blood, tumor, and liver tissue at body temperature 37 degrees Celsius. And the material properties of the antenna, like dielectric, catheter, liver, tumor, blood, at 2.45 gigahertz, because we use here magnetic field. Magnetic field frequency is 2.45 gigahertz, and frequency dependent dielectric properties of liver tissue are also shown here. We consider 4 types of frequency: magnetic frequency 700 megahertz, 2.45 gigahertz, 4 gigahertz, and as well as 5 gigahertz. And then our tissue, liver tissue properties changes, and these are the properties. So all these properties we use, and the governing equations. There are a couple of equations. There are 2 physics actually. First one is electromagnetic wave frequency domain, or geometry, electromagnetic wave frequency. So equation 1, 2, 3 are electromagnetic wave frequency. Here is the electricity part, and here is the magnetic part. So here electric and magnetic, both electromagnetic field we use as a physical model here, and equation 4, 5, all these are the equation we use here, and finally equation 6, and here also electric field strength are given by equation 7. So many equations, and also the boundary conditions for the electromagnetic wave field. The boundary conditions are given here, and then we again use another physics, which is known as Biot transfer. To perform the simulation, we use 2 types of physics. Number 1, electromagnetic wave field, and number 2, Biot transfer model. So Biot transfer model only liver and tumor domain. And antenna domain, and there are only electromagnetic wave frequency models. So we use, this is the Biot transfer equation. What is the difference between heat transfer and Biot transfer model? The difference is that we have metabolic heat source. So in the normal Biot transfer model, there is no metabolic heat source. This part is 0. We do not consider this part. And also this type of Biot transfer model for human body, this is always we use transitional and or unsteady analysis. So here we consider unsteady analysis, because how many seconds needed to abolish the tumor from the liver, it is very important, because for a long time you cannot put the catheter or electromagnetic waves to the human body. The doctor cannot do this. So a particular time is needed, particular amount of frequency is also needed to save the normal cell or normal tissue, because our concern is to abolish the tumor tissue. Okay, but as well as it is also our concern that we do not harm, we do not do any kind of harm the normal tissue. So we have considered two things. One is abolishing the tumor tissue, and another is saving the normal tissue. So what is the magnetic field frequency, what is the electric power amount, and what is the time? It is very much important. And doctor just set all these things, all these three parameters based on the physical condition of the patient. So we just analyze, this is the external part, external heat source part, and this is the SAR. This specific rate for biological tissue. So for direct transfer, these are the boundary conditions, and for dating average heat inside the domain, we can use equation 12, and these are another equation for coaxial antenna, equation 13, equation 14. These are also these equations are well known and are conducted by the research of Gas and Mishra et al. And the solution process. This is the main generation part, and this is the original view. Figure A is the original view, and figure B is the zoom view. This is the antenna, this part is the slot of the antenna. This is the grid sensitivity test showing by this study. We consider 68,289 element for running the simulation and grid test, and also the results are shown as you can see microwave power density. The results are shown by microwave power density. We consider here power, electric power 5 watt to 25 watt. So 5 watt, 10 watt, 15 watt, and 25 watt. And also these are the isothermal lines inside the tumor liver, and this is the elliptic part is the actually the tumor, and the rectangle part is the whole liver. And this is the data plot is in Excel software. We show your transient temperature distribution. We consider 0 second to 1000 seconds. We run the simulation, and time to time you see that when the simulation time increases, your body liver temperature, that means the average temperature of the computational time also increases. So doctors should consider this case also, how much time we need to abolish the tumor step by step. So this is the SAR distribution for considering 5 watt to 25 watt and average temperature. Here we consider only 2.45 gigahertz as frequency level, so magnetic field frequency level. So these are the control plot, and I'm going to the conclusion part. Here in the conclusion part, we show that average temperature of the tumor domain is found 56.86 degrees Celsius at microwave antenna input power 10 watt. 10 watt and frequency 2.45 gigahertz and time 180 seconds. So a small size of tumor will be abolished by this time, 180-second time, if we consider 10 watt power, input power, and frequency 2.45 gigahertz. Then it can be a guide for the doctor also. And then I'm going my another figure. This is the photovoltaic hybrid, advanced hybrid photovoltaic thermal system. You can see there is a house, and at the roof of the house there is a photovoltaic thermal system, and here we can flow cold water, and after passing this photovoltaic module, we can hot water and hot water or heat energy. We can save this heat energy and can use as our household purpose, like taking shower, like cooking, or like dishwashing, etc., or like swimming pool water heating. Many more things we can use. So photovoltaic thermal system is a very important device in the solar energy system. So I'm going to show you the paper. This is the photovoltaic thermal system paper. Here it is published in Results in Engineering by DZR 2025, and here we consider 4E, that is exergy, energy, environment, and economic. 4E analysis and sustainability factors also. So photovoltaic thermal system, all these you can consider here. Our thermal system, just you see, this is the photovoltaic module. Here water inlet. Water is considered as the heat transfer fluid. Water inlet. Here is the pipe inlet pipe, and this way the water goes to this way. This is the water goes, and also geometrical details of the photovoltaic thermal system. You can see this is the system here, and also these are the module cell gaps, and this is the material properties of the photovoltaic thermal system. The model is optical data, operating condition, environmental parameters, all the needed information are given by the tables also. And this is the exploded view of the inlet part, and this is the second inlet position of the thermal system. And we consider the temperature equation. This is the energy equation of solid part, that is photovoltaic part, photovoltaic module part, and the heat exchanger part is attached at the bottom of the photovoltaic layer. So for the heat exchanger part, that is the fluid flow domain, we consider the Navier-Stokes equation and continuity equation, Navier-Stokes equation, and also energy equation for the fluid. So these are the equation 1, 2, 3, 4, and this is the flow chart. How Comsol multiphysics solve this problem, and you see this is the this part I am just showing you in a large view mode. Okay, so this part is the this part is the actually this is the this is the part of the photovoltaic module, and that is glass. Here you see glass. You can see glass also. It is glass. It is EVA, then EVA, then photovoltaic cell, and many more things. A photovoltaic cell, then again EVA, then Kevlar. This part is the photovoltaic module part. This is the solid part. Here heat is transferred only by conduction, no convection. So by solar energy system, here three types of heat transfer occurred. Number one, radiation. Number two, convection, because when we attach the heat exchanger part, then by attaching the thermal test at the bottom of the photovoltaic, then we introduce the fluid we can collect thermal energy. Also, we can collect electrical energy by the photovoltaic part. So, total photovoltaic thermal system, we can collect electrical energy using photovoltaic module, and after that we can collect thermal energy using the heat exchanger system. So using a photovoltaic thermal system, it is known as hybrid photovoltaic thermal system. We can get electrical energy as well as thermal energy. So I'm just zoom out. And there are many equations to calculate the absolute energy, and lost, and some energy is lost by convection and radiation process. So some energy we can collect by convection process. And these equations 6, 7, 8, 9, 10, all these equations we need to calculate the solar system. And how we calculate the sky temperature, this is the way to calculate the sky temperature. Reference 36, we can get this. And detailed simulation part. Now energy and exergy analysis. This is the energy analysis. Equation 12, 13, 14, 15, 16. All these are energy analysis. This is the thermal efficiency. This is the electrical efficiency. And adding thermal efficiency and electrical efficiency, we just we can find overall efficiency of the equipment, of this equipment. Now, energy analysis. So, energy, the sun energy is the thermal energy plus electrical energy plus loss energy. So, equation 17, 18, 19, all mathematical expression, equation 20, 21, up to 25, all these mathematical equations are for energy and exergy related. And for sustainable energy, equation 25 only, sustainable index we can get by this equation. Now, environmental friendly and cost analysis, economic analysis, because we consider here 4E analysis: energy, exergy, environmental, and economic analysis. 4E analysis. So, for this purpose, it is how much it is environment friendly. So, carbon dioxide, how much carbon dioxide it leads to the environment. We can calculate by the equation 27, 28, and also 28, 26, 7, 8, 9, 29, and 30. All these are equation for environment and economic purpose. Equation 31 also. Now, mesh generation and model validation. This is the mesh and mesh full view, and the right one is the zoom view of mesh, and impact of the number of mesh elements. And we can use mesh elements as 30 error percentage less than 136.64%, which is less than 1 to other, and these are the final type of mesh, and 1.52 seconds is needed. And this is the validation part. Validation is conducted by Atia with Atia et al. And these are the results. Manifold height. This height is known as manifold height, and there are the contour plot distribution of pressure distribution. Here we can see the pressure distribution. These are the contour plot. We can show this plot using TechPlot 360, and these are the Excel plot. Excel software generates this plot using the data from the console multiphysics, and finally we can go for the conclusion like this way that in the PBT system with a side entry configuration, a water slick height 1 millimeter, a manifold height 30 millimeter is an effective solution to improve the energy or exergy performance. So we just conduct two types of variation here. One is manifold height and another is slick height. So we conclude slick height is 1 millimeter and manifold height is millimeter. We get it. So do you have more time, or I just go to my presentation at the finishing part?
Ma'am, no problem, ma'am. If you want, you can take till 6 o'clock. That is another 5 to 10 minutes, ma'am.
Okay. 5 to 10 minutes.
For even question sessions, question and answers. If anybody.
Okay, I am going to finish maybe 15 minutes. Give me 15 minutes more, please.
Okay, ma'am. Okay, ma'am. Thank you.
Actually, I am showing here various types of research, what we have done, we have conducted. These are
no doubt it is quite interesting, ma'am. Actually, these are the this is very rare information. They may not have actually. It is very useful information, ma'am. You please carry on, ma'am.
Okay. Okay, thank you. So I'm going to show another work, research work, which is the just taking zoom out. Sorry, this is the two-layered cross-flow microchannel heat exchanger. Ternary hybrid nanofluid. Here we use also 3 types of nanoparticle, and sensitivity study also conducted by response surface methodology. It's a statistical analysis. So after conducting numerical analysis or CFD, computational fluid dynamics analysis, we can get data, many more data, and then we can perform statistical analysis also. Here I am showing such type of research. You can also conduct this type of research for your with your students. Among your students, you can show. Okay, this is the geometry actually. The hot channel layer at the upper layer and the cold channel layer at the lower layer. There are two layers, and the heat exchanger material is stainless steel, and fluid hot fluid is hot and cold fluid are all nanofluid. Same fluid we use at different temperature, cold fluid at 298 Kelvin and hot fluid at 333 Kelvin. And potential application of ternary hybrid nanofluid, you know all these things. And the nanoparticle we use, multi-wall carbon nanotube, boron nitrate, and graphene, 3 nanoparticle, and this fluid as water, and also physical features of solid particle and base fluid. These are the properties of solid and base fluid, and the equations we can consider. The equations are as like this. Equation for fluid domain as well as solid domain. This is the energy equation for the solid domain. Solid material is the heat exchanger material, and fluid domain are the pipe. Inside the pipe there are fluid is passing. And there are also, in between two layers, there is a plate, which is the stainless steel layer. And the effective properties of the nanofluid, this table shows. And this is the shape factor here. We consider spherical shape, platinate shape, and laminar shape nanoparticles. And these are the boundary conditions. And also there are some necessary equations which are very much important to calculate many things of the heat exchanger efficiency. Like Reynolds number, this is hydraulic entrance. We consider square shape geometry here. So this is the hydraulic diameter calculation, Nusselt number calculation. This is the efficiency calculation formula, and also the thermal conductivity part, static part. This is the Brownian motion part of thermal conductivity of nanofluid. And we all consider here. And for this, we consider there is a plate. There is also a plate. Here is a plate, and bottom layer there is a plate also. So this is two layers. So in between two layers there is a plate. You can see. So the plate and the layer solid part are stainless steel material, and inside the hot and cold channel there are hot and cold fluid. So this solid and fluid domain can exchange heat each other, and when the fluid inlet here, temperature increases, but when hot fluid inlet here and outlet by this way, then hot fluid temperature decreases due to the exchange in between solid and fluid material. So these are the cold fluid material thermal conductivity and properties, many more things. And this is the contour plot of different Reynolds number we choose 400 to 40 to 200 as a Reynolds number, that is velocity. You know that when Reynolds number increases, the inlet velocity of the fluid enhances. And after 2000 of Reynolds number, it is the transitional period from laminar flow to the turbulent flow. And after 2300 Reynolds number, it Reynolds number, that is these fluids are laminar flow. It takes laminar flow. So these are the pressure distribution, streamline profile. These are the streamline profile. These are the outlet temperature profile. Only outlet temperature you can see here by this figure, outlet temperature, and these are the data plot. You can see Nusselt number against Reynolds number and efficiency. Efficiency against Reynolds number is shown here. Also the statistical analysis we conducted here using response surface methodology, statistical part. So for this part, this is the polynomial, basic polynomial of this equation, and we consider two independent variable Reynolds number and solid volume fraction phi, and the dependent variable is the Nusselt number, that is heat transfer coefficient, and thermal efficiency. So there are two dependent variables, thermal efficiency and average rate of heat transfer, and three independent variables, fluid velocity variation phi, that is solid volume fraction, and DP, that means nanoparticle size. So we use here box Benton method, BB method. BB is full, it is shortly known as BB is full, and these are the coded value. Lowest value is known as -1, highest value is known as +1, and minimum and middle value is known as 0. So coded value is -1, 0, +1, and actual value is actual, that is CFD value is we consider 222. 200 and like this Reynolds number, and particle diameter 1 nanometer to 10 nanometer. So these are the values for actual values, that is CFD value, and predicted values, that is statistical analysis values. And these are the surface plot of 2-dimensional and 3-dimensional analysis. And this is the ANOVA analysis of variance. We get this equation, coded equation for Nusselt number ANOVA analysis, and for thermal efficiency we get equation 21 for ANOVA Nusselt number and ANOVA table for thermal efficiency. And this is the residual plot, predicted value and actual value for residual plot. This is the actual value, the x-axis is the actual value, the y-axis is the predicted value. And we can show that sensitivity analysis, we conclude this 4, 5, 7 equation, and we show these at the sensitivity graph, the plot. And finally, we go for comparison. As this is numerical work, we have to go for comparison part. And our conclusion show that the R squared, that is the correlation coefficient of the statistical analysis, is almost 0.9, almost 1. Is very near to 1. It is 0.9997. So we get a very good correlation coefficient using statistical analysis. So you can also perform this type of CFD data also, and there are you can see this is solar collector, parabolic trough solar collector for thermal energy storing. Here we can go for this type of research also. This is conference conference published this is published in IOP, Journal of Physics. This year in Japan conference here, I attended this conference and present this paper. This is the parabolic trough solar collector, impact of ion nanofluid. You all know ion nanofluid. What is this? This is nanoparticle and base fluid as ionic liquid, not base fluid as water. From the chemistry department, they all know this type of ion, anion cation. So these are known as ionic liquid. It is not normal salt. It is salt, but not our table salt at dining table. Not that type of salt. This is salt at 100 degrees Celsius temperature. It is melted. It is a melt salt. So we use here nano diamond and boron nitrate as nanoparticle, which are suspended is 1,3-dimethylimidazolium methyl phosphonate DIMIM NOHCO 2. This is known as ionic liquid. These are the chemical names. So chemistry students all know this type of salt name. And this is the geometry. You can see this is the reflector. Reflector, that means the parabolic reflector. And here the sun comes. Reflector gets the radiation, and all from the all sides of the reflector, it concentrates to these absorber pipes. So the backside of the absorber pipe become more hot, and then if we flow inlet fluid, cold fluid, then we get the outlet fluid as hot fluid. So there are various parts of the absorber tube. First of all, glass cover, then copper receiver, glass cover, glass cover thickness. And these are 4 fins inside the absorber. We insert 4 fins inside the absorber. And there are many more tables for data analysis, and all these are the energy conservation, momentum conservation, and mass conservation equation, and many more equations for parabolic solar collector. Here are radiation, convection, conduction, all three types of heat transfer occurred here. So equation 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 13, and 14. All these are the effective equations for these analysis. And these are the boundary conditions and numerical for conducting numerical simulation. We set convergence criteria as 10 to the less than equal to 10 to the power minus 4. When we get this convergence, meet this convergence, the iteration process is stopped and show the results. And this is the validation part, and this is the grid sensitivity part, and these are the results. This is the 3-dimensional analysis. Here we show the 2D view of the result. This is the 3D view. Sometimes we show 2D view to visualize more. So this is a 3-dimensional analysis. And finally, the thermal efficiency improved. When thermal efficiency improved, when we get the higher velocity, we get the higher thermal. The conclusion, we can friction factor decreased by 99.38%, because we need to reduce the friction factor also, as well as increase the thermal efficiency. So there are a few things there are many things, sorry. I am going to finish just showing this picture, this article. You can see this is the heat transfer journal. This is human skin burn intensity. As you know, there are burn accident occurs rapidly in our society. Different types of burn injury we have. So human body, just we consider three-dimensional analysis as well as human skin. It is skin, human skin. The upper part is epidermis, the middle part is dermis, and the lower part is subcutaneous. After that, the inner part of the skin. So we consider a human skin model, and only where we consider the bioheat transfer model. And 4 types of penis, it is known as penis bioheat transfer model. Equation 1 is the penis bioheat transfer model. And there are 4 types of occurrence. We analyze where number 1 for hot unconsciousness, hot dish get touched to our hand skin. So our hand is just burned. how much burn it occurs? That is the analysis part. Another part for hot fluid. Sometimes hot fluid can flow due to accident in our skin, over our skin, and our skin become burn. And there are 3 types of burn intensity in our skin: first degree burn, second degree burn, third degree burn. And here for surface radiation, hot heat transfer occurred. Radiation heat transfer occurred, and our skin also burn, can damage. And last one is the and last one for flash fire. Sometimes in chemical industry or anywhere it can happen a flash fire for few seconds. Flash fire can happen only for 5 seconds, not for many more seconds, only for 5 seconds, 6, 7, 8 seconds, not more for many more time. But by this 3, 4, 5 seconds, great amount or bulk amount of skin of our human body can damage. So these are the boundary conditions for the first and second case. These are the boundary conditions for flash fire, where all the conditions are mentioned, and these are the boundary conditions for radiation. This is the cast iron. This metal radiated heat, and this is our skin. Our skin can burn. So skin properties. We use Arrhenius equation to calculate burn intensity. Hendrix equation, also Arrhenius equation, equation 16, and these are the properties of properties of human skin and cast iron, and other properties at 37 degrees Celsius temperature. We have shown this type of properties, and this is the damage index. Equation 70 is the damage index. That is how much amount of skin damaged. Is this third layer, that is subcutaneous layer, or is this the damage at the front layer? So doctors, when we go burn patients in the hospital, doctors just measure how much percentage is burn of our body, and the burn damage, burn index, or burn degree, how much. Is this first degree, is this second degree, or is this third degree? So third degree burn are more dangerous than first. Okay. These are but we consider 4 different cases. And this is the code validation part. This is also the code validation. This is the surface temperature of 3 skin layers, 3 layers of our skin. This is also the code validation part. Now result discussion, and this is the volume temperature plot with time. We consider here 0 second to 250 seconds, and time, and due to time, increases time, you see that the red part means high temperature part, skin. Blue part means low temperature part, 37 degrees. Red part in high temperature part, it goes down, and this blue part is the subcutaneous domain of our third layer. So this part also become hot, and after 45 degree, we can tolerate 45 degree temperature. Easy after 45 degree, more than 45 degree, that is 50 degree or 55 degree, our skin can't tolerate it. So our skin become burn. So this is the slice plot. You can see the slice plot, how heat is go down from upper skin layer to the inside layer. You can show due to the time. When time is high, then the burn amount is high. So these are the contour plots. You can see I am going to the section of damage. So it's a different point from top to the bottom layer. We take 0%, and at the top layer of our skin, the damage is almost 100% at 50 degrees Celsius. Hot dish 50 degrees Celsius, our soft layer of the skin become highly damaged. So this is the burn intensity part, and here we can calculate the burn relationship between time, temperature, and burn intensity. When burn intensity increases, for this time also increases and temperature also increases. So these are the comparison among our results and also published results, and this is the published results comparison, and major outcome is the severity of skin burns caused by direct contact with a hot dish is greater than that caused by free flowing hot fluid in terms of burn injuries. Okay, so I am going to finish my presentation. Thanks to all. Actually, I take too much time. Many more things I want to show you, but due to time limitations, I can't. Okay, another illustration I can show you. Thank you.
Thank you very much, ma'am. Such a wonderful session actually we had today. And you started from the beginning, that is the basics of computational fluid dynamics, to you explained what are the suitable methods, even the modeling how to do, and in detail how to do even a research paper, and also you shared the recent research work also. I hope all the audience will utilize this one very well, and in a single word we can say, by attending this session, any scholar in a mathematics, they can do comfortably, they can do their work in computational fluid dynamics. Such a wonderful session we have, ma'am. Thank you so much, ma'am, for sparing your valuable time and giving very informative things to our audience. Thank you so much, ma'am. Thank you once again. Now,
any question? Can I stop sharing?
Please.
Okay. Any question, please?
Questions, please.
Who are interested can connect with me by email or over WhatsApp. Any interested person can connect.
No one is asking, ma'am, but while delivering your lecture, somebody asked one question, that is it only the boundary conditions matters? They posted in the chat box actually. Boundary conditions is everything, or anything else we have to take care of? That the question they ask, ma'am.
Not only boundary condition. If we consider our analysis is unsteady analysis, that is time dependent analysis, then we have to consider initial condition also, and boundary condition, of course, boundary condition, but also initial condition. But if we consider our analysis is only steady state analysis, then we do not make any tension by taking any time variable. So the time is not dependent variable that time. Independent variable not. So it is easier to consider steady state analysis.
Thank you so much, ma'am. Thank you so much, ma'am. No other questions. We cannot see anything on chat box also. Thank you so much for sparing your valuable time once again, ma'am. Thank you. So, as a convener remarks, I can say that really these 2 days, I hope you enjoyed, all the participants enjoyed a lot, and I'm happy to say that more than 740, nearly 745 registrations for this international seminar, and yesterday also good participation we can see, and participants are also from various states of this country, not only from this country, and we can see participants from South Korea, Oman, USA, Bangladesh, and Nigeria. So this is the response what we have, and feedback form is shared. So please share your feedback through the feedback link which we shared now. That helps us if anything you want in the further field also, in which direction you want the sessions and all. If you give such a feedback, that really helps us a lot. Thank you all for your patience listening and making this program a grand success. With these few remarks, may I now invite Dr. Mallipriya to propose formal vote of thanks.
Good evening to everyone. On behalf of the organizing committee, it is my privilege to propose the vote of thanks at the conclusion of this international seminar, Computational Techniques in Mathematics. First and foremost, I express my sincere gratitude to our Honorable Vice Chancellor, Professor S. Prasanna Sri Madam, for her constant support, guidance, and encouragement. My heartfelt thanks to our Registrar, Professor K.V. Swami Sir, and Principal UCST, Dr. P. Vijayanagala Madam, for their valuable support and presence. Our heartful appreciation goes to the esteemed resource persons, Professor D. Srinivasacharya, Department of Mathematics, NIT Warangal, and Dr. Rehana Nasreen, Professor, Department of Mathematics, Bangladesh University of Engineering and Technology, who enlightened us with their expertise and insights. A very special word of thanks goes to our convener, Dr. T. Haimavati, whose vision, commitment, and tireless efforts have been the backbone of this seminar. I extend thanks to our co-conveners, Dr. K. Ravati, Madam, and Mr. K.V.M. Varkumar, sir, for their able support in making this event a success. I sincerely acknowledge the dedicated efforts of the organizing committee, and I thank all the participants and delegates for their active involvement and crucial in making this program success. A special thanks is reserved for our technical staff, K. Girdhar Sai, P. Sunil Kumar, whose expertise and constant support ensured the seamless conduct of every session. I extend my sincere thanks to the print and electronic media for their coverage, in particular PRO Anand sir. Finally, a special thanks to the students who worked behind the success to ensure smooth conduct of this program. Thank you one and all. Thank you, Convener Dr. T. Haimati Madam, for giving me this opportunity. Thank you.
Thank you all. We will conclude this
Thank you
session
all.
by our national anthem. Ma'am, anything you want to say, ma'am?
Oh, thank you very much.
Yeah, now we will conclude this session with our national anthem, ma'am. We will rise for national anthem.
Thank you.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तब शुभ आशीष मागे गाहे तब जय गाथा जय गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे. Thank you all. Thank you, ma'am.
Thank you.
Thank you.
Okay. So I'm leaving.
Yeah, thank you, ma'am. Thank you.
again.
Yeah. So all the participants, please fill the feedback form that is posted in the chat box. It will be kept for 1 hour, and after that it will be removed from the thing. You please take care of that. And once again, thank you all for making this program a grand success.